Assalamualaikum, and we're from Group 5 are going to present our group project assignment, and the topic that we chose is population in Nigeria. I will pass the introduction part to Izzuddin.
Thank you, Haikal. Now we go for my slide. This is our content. As you can see, our group member is me, Izzuddin, Adib, Haikal, Abdullah, and Afnan. Task 1 is application of first order differential equation. This is our introduction. In this task, we were to use first order differential equation to find the growth in population of Nigeria. We find population data set from 2000 to 2020 and plotted graph to represent the growth of the population. We also calculate the estimation of the future and past value using the formula P equal to AEKT. Thus, this task is carried out efficiently to fulfill the objectives of the MAT099 project assignment, which are CL02, PL03, CL04 and PL07. In this project, all of us are required to study the application of first order differential equation. This is our objectives for the task: to find a particular solution of differential equation for the population in Nigeria from 2000 to 2020, to predict the future value using particular solution and compare with the historical data, to predict past value using particular solution and compare with historical data. Population in Nigeria statistic table is given as this. We claim the data from a website. There's the two problems we choose, growth or decay. So we growth from this data we got. Now I pass to Abdullah.
Okay, thank you Izzuddin. And now we move to our next part, which is graph. As you can see, this is our graph, and the red line represent the estimated value and the blue line it represent the actual value. So we move to our next part. The estimation calculation. The estimation calculation used is the formula P equal to AE the power of KT. So we substitute T equal to 0, which is for year 2000 into the formula. Then we got the constant A, which is 126,382,494. We substitute T equal to 1, which is for year 2001 into the same formula, and then we got the constant K, which is 0.027,163,95. Then we got our formula in this calculation is PT equal to 126,382,494, the power of 0.0271,6395 times T. Our next part is step 4, which is future value. We substitute T equal to 21 into the formula, and then we got the value is 223,577,012. And step 5 is the past value. We substitute T equal to -1 into the same equation, and we got 122,995,654. This is our percentage error. We use formula estimated value minus actual value over actual value times 100%. The percentage error we got is in the range of 0 until 1.7%. So we move to our next part, which is Haikal.
Thank you to Abdullah for the brief explanation just now. For the discussion, I'll be answering 5 questions. For the first question, are the value calculated from the particular solution accurate with the actual value? And for the second question, find the percentage of error, if any. The values calculated from the particular solution is quite accurate to the actual value, and the percentage error that we got is within the range of 0% to 1.7% for each year. For the question number 3, if there is any difference between the actual value and the value calculated from the particular solution, why do you think it is so? We think that the difference between the actual value and the calculated value might be due to several reasons, one of which is sampling error or the data error, which means the data is collected from sample rather than the entire population. From the calculation, it may be caused due to rounding of the value. And for question 4 and question number 5, what has affected the population growth in the past, and what do you think might be affect the population in the future? The effect of the population in the past and future might occur due to inconsistent mortality rate, fertility rate, birth, death, and migration, which can vary and kept the population increasing. Now I'll be talking about the conclusion of the task. As we can conclude, first order differentiation can be realistically used to predict future population for any country with minor error. This provides a range of possibility to help in future development of a country. Plus, with such a low percentage error, it's a great method to be used when conducting any prediction of a value for population or other things. I'll be passing task 2 for Adib to explain.
Thanks, Haika. Now we'll move to task 2, which is numerical method. For this task, we will task to determine the integral of square root 5 ln x squared plus 2 plus exponent to the power of x cubic using trapezium rule with 6 and 8 sub-intervals. And for my part, I will be explaining the 6 sub-intervals. Here is our Excel spreadsheet. First, we write down the lower boundary as A, which is -3, upper boundary as B, which is 1, and the number of sub-intervals used here is 6. Then we can calculate the delta x, which is B minus A divided by n. Next, we'll move to the x values. First, we start with lower boundary, which is 3, and we increase it by increment of delta x, which is 0.67. Next, we can get the fx value by substituting the x value into the equation earlier. And for the coefficient, for trapezium rule, the coefficient is actually standardized, which is the first and last coefficient is 1 and the rest will be 2. And we can calculate the coefficient times fx. And the total sum of the coefficient times fx is 37.63. And by dividing this total into 2 and timing it with delta x, we can get the area under the graph. Okay. So here is our graph for 6 sub-intervals. We use an application called Desmos, and as you can see, the area under the graph is divided into 6 regions representing the 6 sub-intervals. That's all from me. Now I'll pass to Afnan.
Thank you, Adib, for the explanation of the 6 sub-interval. So moving on to the next part, which is 8 sub-interval. So we use the same value of upper and lower boundary, which is -3 and 1, but the difference is the value of n, which is the sub-interval we use, is 8. So the delta x calculated is 0.5. So in the 8 sub-interval, we have a total of 8 value of x. So each of the coefficient same as the 6 sub-interval. The first and the last coefficient is 1 and the rest is 2. So the sum of the function multiplied by the coefficient is 49.68814. So by using the formula, we multiply it with delta x and half. So we got the value of 12.42204. So this is our visual graph. So as we can see here, the number of sub-intervals is more than before. So each of these region represents to calculate the area under the graph. So the 8 sub-interval is more accurate than the 6 sub-interval one. So the value between 6 and sub-interval is different because the higher the number of sub-interval, the more it will cover the area under the graph. Or in other words, the closer it is to the actual value, which is 12.24523. So what we can conclude is the 8 sub-interval is more accurate than the 6 sub-interval. So I think that's all. I will pass to Adib for the end part.
Okay, thank you, Afnan. Now our presentation has come to an end, even if it was short, but the memories we spent together will always be ingrained in the back of my mind. Dah.